This is example 7.3 from chapter 7, not reserve problem, but example 7 that's described in the chapter. So far in the previous videos, we've seen, we've just applied the Taguchi function, loss function, but here in this problem, we're actually given dimensions or a probability of actual values for a quality characteristic that has been produced using two different processes. So it says here that here's the statement of the problem. Two processes have the following distribution of quality characteristics. So we have dimensions and probabilities for each of them indicated. The specification is 0.05 plus or minus 0.02. So there's our nominal and our range of tolerance. Output of A ranges from 0.48 to 0.52. You can see that outside at 0.47 and 0.53, it's 0. So that process produces products that are between 0.48 and 0.52. And these are the associated probability of those values. And output B ranges from 0.47 to 0.53, but the probabilities are different from one value to another. Notice here these are all uniform or equally likely. And so you can see that over here the probabilities are much higher when you're around the 0.5, which is the nominal value of our quality characteristic. Okay, so the loss function is given to us right here, and we want to be able to compute the expected loss for each process so that we can see which process is better in terms of monetary consequences. So in order to compute the expected values, we can, well, to compute the expected value of each of the processes, we can use a sum product, product of the dimensions and the probabilities. And we can do the same thing here. Sum product of the dimensions and the probabilities. So we can see that the average value or the expected value of both of the processes is 0.5. But there is variation. We can tell that there is variation because the probabilities are different. So in this case, what we want to do is to compute the squared difference between the expected value and each of the process values or values of the random variable. So in this case, we want to take each of the values of the random variable for process A and subtract from it the expected value. I'm going to fix the cell reference. And then square that, so we have squared deviations. And that formula can be copied down. And the expected variance is essentially the sum product then of each of the probability values for process A multiplied by this squared deviation that we have here. So so we have sum product of the probability for process A multiplied by the squared deviation of process A values from its expected value. And we can do the same thing here. Oops, I didn't. That's okay. I can go ahead and do this and then write these values or compute those values. So I'm going to do the square differences here. And that is this value minus, oops, yeah, minus the, I'm going to fix the cell reference and square it. Forgot my parentheses. Okay, so we're going to do that, and we get 0.0009 here. So then the expected loss is going to be the it's going to be the well, actually, I'm going to do this one later. Right now, I want to compute the expected values, or I'm sorry, expected loss for each of these. So I'm going to copy this down here, and I'm going to say loss based on our loss function is going to be equal to 125,000 times our x value right here minus our, I need to put the parentheses, our x value minus this nominal, which is our target value. But I'm going to fix the cell reference, and then I need to square that. So if I copy that down, then given that the probability of process A is these ones right here, the expected loss is going to be some product of these expected losses or loss values and these probabilities, which is $25. For probability of process A, we have these probabilities. So the sum product of the loss values and these probabilities for process B will be 1125. I think I typed this wrong. This should be B. So comparing these two, you can see that this process B has a much lower loss per expected loss per unit, even though two of its possible values fall outside of the range of tolerance, because our tolerance, if you remember, is right here. So our range is going to be from 0.48 to 0.52. So these two numbers fall outside of the range, but even with that, this value, expected loss, is lower. Now your book says that all of this can be minimized by using this function. The expected loss is equal to our k constant times sigma squared plus that difference or deviation squared. So, so in this case, we have our expected loss that we can compute. It's equal to our K, which is 125,000, times our sigma squared or variance, which in this case is this number right here, plus the difference of our expected value, which is 0.5, minus the target value. Squared, which is 25. And I can do the same thing here. Again, it's 125,000 K, which is this number right here, times, did I move the cursor? Yeah, is equal to 125,000 times the sigma squared, which in this case for process B is this number, 0.00009, plus the difference between the x value, which in this case the x value is our expected value for this process, minus the nominal value or the target value, which is for this whole production is 0.5, which is there. And that number is squared. And that gives us the 1125. So either way, we get the same answer. But as you can see, this process B is much more economical or affordable, given even though the range of tolerance is exceeded in its production, but overall it makes more economic sense. Thanks.